So here we're starting the origins of the elements. These are the NISA outcomes, and I've highlighted particular phrases that we'll deal with as part of this topic. And we're starting to investigate the processes that led to the transformation of radiation into matter that followed the so-called Big Bang. So we're learning to analyse the properties and processes occurring in main sequence and post-main sequence stars, and we will be able to analyse and apply modern concepts to stellar observations and ideas about universe origins. So let's have a think about the transformation of radiation into matter after the Big Bang. Now, galaxies outside the Milky Way are moving away from our galaxy in general. There's one or two that are moving towards us, but according to the Big Bang theory, if time is run backwards at some instance in time, the universe and everything in it was contained at a single point, sometimes called a singularity. Everything was essentially made from nothing in one Big Bang, and this aligns with both the Big Bang theory and a biblical perspective of origins, where God said, "Let there be light," and then there was light. There are two concepts that explain the process which led to the transformation of radiation into matter that you need to know about. The first is inflation, and the second is matter and antimatter. So inflation. To explain the initial stages of the Big Bang, scientists describe a period of rapid inflation right at the beginning. This period only lasted around 10 to the negative 24 seconds, but in that time, the universe expanded to 10 to 50 times its original size. This period was necessary as a rapid inflation in order to prevent the initial universe from collapsing back into itself as a black hole. However, if the inflation had lasted any longer, atoms would not have been able to be formed. And matter and antimatter. Following is according to Big Bang theory. When particles are created, they always come in pairs. So for every matter particle created, there is an antimatter particle. However, because they are so close together, they annihilate each other immediately after coming into existence. As two particles are always produced in this process, it's called pair production. Due to the annihilation effect between matter and antimatter, normally pair production does not produce any lasting matter. However, the period of rapid inflation that we just talked about meant that the matter and antimatter particles are driven away from each other before this annihilation can occur. Hence, within that small time frame, a large amount of matter was created. In the first few moments after the initial creation of the universe, particles and antiparticles annihilated each other to produce high-energy gamma photons. These high-energy photons collide with each other again to form new particle pairs. Here's a photo of Edwin Hubble. He was born in 1889 and died 10 years before I was born. The photo shows him looking through the 100-inch telescope on Mount Wilson in the USA with a camera attached. And he provided the first real understanding of evidence of the expansion of the universe. He took long exposures of the spectra of faint galaxies and measured the amount of shift of specific spectral lines relative to those produced by reference arc lamps in the spectrograph, and he was able to calculate values for the galaxy velocities. A few nearby galaxies had velocities that meant that they were moving towards our own Milky Way, that is, their lines were blue shifted. But most galaxies exhibited redshift and hence had recession velocities. The majority of galaxies therefore appeared to be moving away from our own galaxy. Hubble found that those with smaller image in the photograph had higher redshifts. And so he came up with some evidence that supplied support for the model of the universe that we call the Big Bang model, or sometimes the Big Bang theory. In the top right-hand corner, there is a graph of the intensity of cosmic microwave background against wavelengths, and that's the second thing we'll look at. The first is the observed recession of galaxies. Most galaxies, and certainly the more distant ones, exhibit a higher redshift of their spectral lines than closer galaxies. So the more distant galaxies are receding from us faster than the closer ones, and we call that now Hubble's law, and that's due to the expansion of space according to the Big Bang model. The second evidence is the cosmic microwave background radiation. As the universe expanded, it cooled, so that today the background radiation corresponds to a temperature of around about 2.725 Kelvin and has a black body spectrum. And you can see that shape in the graph on the top right. The third evidence is the ratios of primordial elements, or so-called primordial elements. Astronomers are able to measure the relative amounts of the light in clouds of primordial gas, and the relative abundances of these nuclei correspond with predicted ratios from the Big Bang model. In other words, hydrogen and helium occurs more in the universe than other elements. The fourth evidence is the observed evolution of extragalactic objects over cosmic time. So recent observations by the Hubble Space Telescope and other telescopes have provided our deepest ever views of the universe and clearly show evidence of galactic evolution and earlier stages in their formation. Those 4 points you need to learn as evidence for the Big Bang model. Here's a plot of recession velocity in kilometers per second of various galaxies against their distance in megaparsecs. And so you can see the diagram on the left shows a photo of particular clusters and on the redshifts are shown on the spectral lines, and in between there's the distance in light years, and those have been plotted on a few others, and there is a line of best fit that shows that the recessional velocity is proportional to the distance to the galaxy. And that line of best fit is called Hubble's law. So Hubble's constant is that slope of the graph. Hubble's distance-velocity relationship for galaxies is now known as Hubble's law in his honour, and is interpreted as evidence for an expanding universe. Hubble realised that he could fit a linear relationship to his data, as shown by the pale blue line of best fit on the previous slide. The slope of this line is a constant that's now known as Hubble constant, or H0. This relationship is then expressed mathematically as V is proportional to D, or V equals H0D, where H0D is Hubble's constant, V is the recessional velocity, and D is the distance. The Hubble Key Project team used the Hubble Space Telescope to observe Cepheids in galaxies and calibrated their values with other techniques. And they obtained a value of H0 equal to 70 kilometers per second per megaparsec, plus or minus 10% error. Well, what do we do with that? Here are some worked examples, and these slides have more details if you go to the physics website, but I want to take you through some worked examples using Hubble's constant. So to use Hubble's constant, and there it is, to find the distance in megaparsecs of a cluster galaxy in Boots that has a recessional velocity of 39,000 kilometers per second. Well, here's the data. It's always the first step. And of course, we're going to use Hubble's law and substitute. And we simply put in 70 because that's what we're given, and the 39,000. Divide, and we find the answer in megaparsecs, correct to 3 significant figures, is 560. But what's this in light years? Because remember, megaparsecs is used specifically for Hubble's law, but we deal with things in light years, and 1 megaparsec is equal to approximately 3.26 million light years. So we just simply multiply, and we find that the answer is 1.82 times 10 to the 9 light years. Well, let's use Einstein's energy mass equivalence equation and apply that to stars. So Albert Einstein described the equivalence of energy and mass as E equals mc squared, most famous formula. And the mass of a helium-4 nucleus is slightly less than the sum of the 4 separate protons and neutrons needed to form it. In nuclear physics, the masses dealt with are so small that the atomic mass unit, or AMU, or simply U, is what we use. And you can find what that is in kilograms from the data sheet. So a proton has a mass of 1.0078 AMU. So 4 protons add up to 4.0312. A helium-4 nucleus has a mass of 4.0026, which means that there's a mass defect, and the difference between these total masses is 0.0286 AMU, or only about 0.7%. That difference matters because we use E equals mc squared, or rightly E equals delta m c squared, the change in mass, and we multiply out and we find the energy in joules of that mass defect is 4.3 times 10 to the negative 12. And that's to 2 significant figures. Now note a couple of things here. 10 to the negative 12 is very small, and yet it's still the whole thing is a positive number. So we have positive energy being given out from this mass defect. So the production of each helium nucleus releases only a small amount of energy, and it doesn't seem a lot, and yet when that happens over and over and over again, we get a huge amount of energy released. So how long will the Earth shine, how long will the sun shine? We know that the measurement of the sun's luminosity is 3.9 times 10 to the 26 joules per second. So every second, 3.9 times 10 to the 26 joules are being produced in light energy. To produce this amount of energy, vast numbers of helium nuclei must be formed every second. And there's a simple division we can do to find 9 times 10 to the 37. So each second, 600 million tons of hydrogen fuse to form 596 million tons of helium. This means that 4 million tons of matter is destroyed and converted into energy each second. 4 million tons. Now, those are not metric tons because I sourced this from, you can see the source at the bottom of the page. The high temperature needed for this hydrogen fusion is only found in the core of the sun, and only about 10% of the total mass of the sun. The energy available from this mass of hydrogen is roughly E equals mc squared. So the mass defect per helium nucleus produced times c squared times that mass of hydrogen in the core. So again, we substitute, do the calculation, and it's 1.28 times 10 to the 44 joules. If a nucleus is stable, its mass is less than the sum of the masses of its components, and the difference, called the mass defect, or delta m, or the binding energy, is then E equals delta m c squared. Given that the sun's energy output currently is 3.9 times 10 to the 26 joules per second, and assuming that it will be roughly constant for the main sequence lifespan, then the sun has enough core hydrogen for about 10 billion years. It's a little bit more than my lifetime. So here's another worked example using this idea of mass defect. And just have a quick look at the diagram at the top of the right of the screen. It's obviously trying to get a concept across. It's not meant to be realistic at all. But let's supposing we have 2 protons sitting on the scales and they're not joined together. That gives a certain mass. When they join together, there is a mass defect. In other words, they will way less, to use colloquial terms. That mass defect is its binding energy. Now, the question is to calculate the mass defect and binding energy in joules for one proton and one neutron that fuse to form a deuteron. Now, deuteron is an isotope of hydrogen. It has two particles in the nucleus, or two nuclides. And we're given the mass of the proton, that's on the data sheet. We're given the mass of the neutron, that's also on the data sheet. But we need to know, and this has to be given in the question, the mass of a deuteron is 2.0141 atomic mass units. Note that a deuteron is stable nucleus of deuterium, which is an isotope, and it has a proton and neutron joined together by the strong nuclear force. So here's the data. I won't repeat it. Here's the formula. Please notice this is not on your formula sheet. So the change in mass is the mass of the proton plus mass of neutrons separately. Take away the mass of the deuteron. That's the nucleus of the deuterium atom. So when we substitute those values, it's a simple calculation to find 0.00190 atomic mass units. Then we use that in E equals delta mc squared, and again substitute, calculate to get 2.84031 times 10 to the negative 13 joules. Well, let's have a look at worked example 3 to do with spectra of light. And you can see already I've put a diagram there showing the black body radiation of the incandescent light. That's the pink curve. But it also shows a few other things, such as sunlight at noon, as we have it on Earth. It's got the spectrum of white emitting LED and compact fluorescent, which are the green spikes. This is a question that came in the 2020 HSC paper. It says, describe the difference between the spectra of light produced by a gas discharge tube and by an incandescent lamp. Now, please note, in the HSC, there was no diagram or graph. So we want to make sure get these 2 marks, don't want to throw them away. And here's how a sample answer would start. Light from an incandescent lamp produces a continuous spectrum. That's the smooth one. The graph shows the incandescent lamp in pink, following a black body continuous spectrum with its peak in infrared. Please notice the highest point on that graph is beyond visible light. Light from a discharge tube produces a spectrum composed of only a few discrete wavelengths of light. The graph shows the discharge from compact fluorescent, that's the green, and white emitting LED, that's the blue. Both have shorter range of wavelengths and discrete peaks. That's fairly obvious from the compact fluorescent. Now, I've written that sample answer based on the graph, but of course in a HSC you may not have a graph to refer to, but you can draw one. Let's have a look at worked example 4. Properties of stars. Star A has a peak emission at a wavelength of 550 nanometers, whilst Star B has a peak emission at 480 nanometers. What can you deduce about the stars based on this information? Well, firstly, the data, we'll call it lambda A, 550 nanometers, and lambda B, 480 nanometers. Always worth writing down data. And we can find the formula from our formula sheet. Lambda max equals B on T. Remember, T, capital T here is the temperature, the surface temperature of a star. Therefore, star B's peak emission occurs at a shorter wavelength or higher frequency than star A, so it is likely to have a higher surface temperature. That is, TA is greater than TB. Star A is hotter than star B. Thus, star B would also appear to be bluer and brighter, if similar distance from the Earth, than star A, which would appear similar to our Sun in colour. Well, let's introduce the Hertzsprung-Russell diagram. And I've put an example here that I think you should learn, and you'll see variations of this, but this is the easiest one to understand what it's about. There is a link at the bottom of the slide here if you want to follow another way of explaining it. The Hertzsprung and Russell were scientists who independently developed versions of the diagram that plotted known stars according to their luminosity and their colour. And different stars plotted labelled different letters on this diagram. So A are the main sequence stars, B are red giants, C are red supergiants, D are white dwarfs, and E blue giants. Now please notice that there are 4 axes, and effectively the colours, which are called spectral class on the bottom of the graph, line up with effective temperature in Kelvin. And please note that this is not a linear scale, and also note it goes from hot to cooler. So stars that have a surface temperature around about 3000 degrees, or 3000 Kelvin, are actually on the right-hand side, whereas stars that have a surface temperature of 25,000 Kelvin are on the left-hand side. But also there is an absolute luminosity or brightness. The brightness is called absolute magnitude. And on the right-hand side, you can see it's called luminosity, and it's formed as a fraction relative to the Sun. So the Sun has a luminosity of 1, and anything above that have a higher absolute magnitude brightness, which means they have a higher luminosity. And everything lower, of course, has a lower luminosity. Well, let's deal with a worked example using the Hertzsprung-Russell diagram. And it says, use the HR diagram, that's how it's abbreviated, to determine the properties of Betelgeuse. Now, Betelgeuse is in the constellation Orion. There's a picture of it in the bottom right of the screen, and that's the way we would see it in the southern hemisphere. Betelgeuse is an M spectral class red supergiant, and we want to find out its temperature, its absolute magnitude, and its luminosity. Well, if it's an M spectral class, we go to the HR diagram and we see on the right-hand side at the bottom, everything there is an M class star. And it's a supergiant. So supergiants, remember, they're the ones up the top. C are red supergiants. E, they're all the blue supergiants. So for Betelgeuse, it has to be somewhere in the temperature range on its surface of 3000 Kelvin. That's the first thing. Secondly, it's using the axis on the left, the absolute magnitude is negative around about 6. And then using the right-hand axis, its luminosity is greater than 10 to the 4 L Sun. That's the symbol for the Sun. Well, let's look at worked example 6, again using the HR diagram. And we're going to rank the following in order of increasing luminosity. So we have a blue supergiant, the Sun, a red giant, and a white dwarf. Increasing luminosity is on the vertical axis on the HR diagram from the dimmest to the most luminous. Have you worked it out? The dimmest is the white dwarf. And we're working up the diagram. So the next would be the Sun, then the red giant, and then the blue supergiant. So in other words, D, A, B, E. Here's a diagram that's very, very important, and it shows the change of 4 different stars. They're on the left-hand side. So we start with a red dwarf. Over time, if it's a red dwarf that's over about 0.8 of the mass of the Sun, it will just continue to be a red dwarf, and then fade to a white dwarf right at the end. So as you go from left to right, that's the time. The second one is a main sequence star, so similar to our Sun. but it's under 4 times the mass of our Sun. So it's somewhere between 0.8 and 4 masses of the Sun, or solar masses they're called. Well, what happens to this? This is what will happen to our Sun, according to this. It will then, at some point, from being a yellow star, it will use up its hydrogen and convert it to helium, and it will eventually blow up into a red giant, which will then form a planetary nebula. Now, that's not planets, that's just a huge hot gas that just keeps expanding. What's left in the middle is a white dwarf. What happens to stars that are greater than 4 solar masses but less than 25 solar masses? And that's the third one. Again, they'll go through this burning up of hydrogen, so-called burning, to form helium, but at some point it'll run out, and in a shorter amount of time it'll turn into not just a red giant but a red supergiant, and it will go supernova. In other words, it'll explode, and huge amount of energy is released, and the core of it will then collapse into what's called a neutron star. It's a star that rotates very, very fast and is only made up of neutrons. It's very, very dense. If a star starts its life greater than 25 solar masses, it again has a shorter life, and it will turn into a red supergiant. It'll go supernova, similar to before, but this time the center is so dense that it keeps collapsing in on itself and getting denser and denser until nothing can escape, including light itself. Now, it's called a black hole, but I like to think of it as a black star. In other words, it's a star that's incredibly dense, but not even light can escape from it. So, what is a supernova? On the 23rd of February in 1987, astronomers were not expecting this. They took a photo into this beautiful nebula and galaxy. But then they noticed this. There was a star that had gone supernova. In other words, it went in one of the brightest supernovas ever recorded in history. So it's an explosive end of a star's life. And during the first 10 seconds of a supernova core collapse, it radiates as much energy from the central region of 30 kilometers across as all the other stars and galaxies in the rest of the visible universe. That's phenomenal, just in 10 seconds. Supernovae are the primary suppliers of heavy elements of the universe. Elements such as carbon, oxygen, and iron are produced by nucleosynthesis within the star. The amount of heat and pressure released from a supernova explosion may create new regions of starbirth by compressing the surrounding interstellar medium. Well, let's have a look at worked example 7. Explain the death of a main sequence star with solar mass between 0.8 solar masses and 4 solar masses. And this is how we do it. A star begins to die once it converts all the hydrogen in the core into helium. As hydrogen is used up in the inner core, this causes the inert helium-rich core to begin to collapse due to gravity, and thus releasing more energy. This energy quickly heats up the outer hydrogen-rich layers and causes nuclear fusion of hydrogen in a thin shell immediately surrounding the core. As this process continues, the hydrogen-fusing shell migrates outward and causes the outer layers of the star to heat up. The increased outward pressure causes the whole star to expand into a red giant.